Hello there. Welcome to another physics session. I've been actually sick for a while, and thank you for those of you who wrote to me to restart this problem and concept clarification videos. Okay, so today we are going to look at a concept called Brewster's Angle. This also called, by the way, polarization angle. Okay, polarization angle. And rather than give just the formula for this angle, you need to understand the concept behind it. Okay, so concept behind it is like we look at a reflection of light. So reflection happens when light strikes the interface between two media, right? Not just from the mirror. This mirror is basically two media. You have air, and then you have a silver, another medium. So there's interface between the surface of silver is the interface, and so silver will be another medium. But in general, we can just look at two medium. So we have a medium, refractive index N1, and medium with reference N2. So, so this was glass and this is air. Then we're going to talk all the formula in terms of this ratio N2 over N1. So this is a case where you have air and glass, then this is greater than 1. And the light is coming from this air part. So this is called external reflection, and light comes in. Some light, this is the intensity of light, comes in and then reflects off, and some goes into the other medium. This also happens in the silver, by the way. It goes in a little bit, goes inside the silver. Now if you think about another, so this is glass and this is air again, but incidence beam is traveling in the glass, hits the interface, some gets reflected back inside the glass and some gets transmitted in the air. So this is called this kind of reflection is called internal reflection. Okay, and this kind of called external reflection. And so when you do an experiment like that and you just look at how much of light you got over how much you sent in, intensity ratio, so that intensity we call reflectance, and then you can do this experiment. Maybe you have a detector, you already know the intensity of that, and you can say how much I sent this much intensity, how much came in here, and the rest must have gone inside there, right? Or you can do another detector, but we're just looking at one detector here, and this ratio is R. You plot, you might find, this is kind of roughly what you might find. You will find that the light kind of has a dip at some point, not quite zero because this is unpolarized light. We'll see at if you have certain kind of polarized light, this will become zero, but for unpolarized it's going to have a dip. And then if you keep raising the angle of incidence, so you start from 0, so this is the angle 0, and then bigger angle of incidence. As you get past this angle, you also rise again, and when you suppose you're shooting from this direction, of course this everything gets reflected. So this is 100. So this is what you might find for external reflection. And for internal reflection, something more happens, right? You might already know there's something called total internal reflection. If you have this kind of situation, so incidence in the high refractive index, it comes in. This is a bigger angle than this angle. So eventually, when you keep going up, at some point, it comes out like that. So that's a critical angle. So here, there's a dip at this special angle, and then there's another special angle at which beyond which it all gets reflected. there's nothing in the other medium. So here there's no such thing. There's no second special angle. So this first special angle, this is the Brewster's angle. And this second, so these guys are Brewster's angle, and this guy is critical angle. Okay, now question is why there is a dip. Okay, and for that, to understand that, we have to look at polarization of the light. So I'm going to change the video to another slide. Okay, so if you instead of totally unpolarized beam, you do the same experiment. So we're just going to do external. Both of them are illustrated as an external. N2 is greater than N1 here. So there you can have this word polarization. Polarization, you might remember from prior videos that I had about polarization. The polarization refers to the direction of electric field for the electromagnetic wave. So you look at light as electromagnetic wave. So if the light was traveling this way, so this is direction travel, then the electric field has to be in perpendicular to this. So if this is direction travel is z, then this is in the xy plane. So electric field may be pointed like that, and magnetic field will be used right hand rule. Magnetic field will be pointed this way, perpendicular to that. So at that point, the other point, electric field may be over here. Electric field may come down like that, may be pointed this way, and then you'll have to use right hand rule again. And so if the electric field is this way, magnetic field is that way. It's still xy plane. So if you look inside here, then there is a plane perpendicular to that. Okay, so magnetic field is perpendicular to this. If this is xy plane, this and this are in xy plane, so that will call it the plane of incidence. So magnetic field is perpendicular to that, then that's called transverse magnetic polarization. If electric field is perpendicular to that, then we call it transverse electric polarization, or TE. And you can see from these two, if you have an unpolarized light, then you can write some will be of this type and some will be of this type, and there will be some of the two. So if you have some unpolarized, you can actually make it how much is in the TM and how much is in TE, because electric field have to be somewhere. In here, electric field is in the xy plane. So say this is x direction and this is y direction, then it's in xy plane at some angle, and over here this is y and this will be x. The electric field is out of the plane, so together these two vectors will make up the electric field in a random direction. So if you have electric field in random direction in this plane, then you can sum up you can write the electric field in the z direction and plus electric field in whatever the, direction this happens to be at that point. Okay, so having said that, we don't need to worry about that anymore. So you can apply Maxwell's equations, use Maxwell's equations to derive what is called Fresnel equations. So equations or relations. So if you say prime for the reflected and unprimed for incident, then the ratio of the electric fields, not intensity anymore, because you're using Maxwell's equations or the laws of electricity and magnetism, and what happens at the boundary. There's a relationship between what the electric field is this side or electric field this side of the boundary is, and these relations come from those boundary conditions, and you can derive this, and more advanced books do have the derivations. Okay, for instance, if you look at Hecht books on, say, optics, that will have it, and there are many other books. This is a very good book though. So if you do the transverse magnetic, you get this relationship. If you do the same calculations, what's the relationship between the reflected electric field and transmitted electric field? Same. You can also get the relationship with magnetic fields, but I'm just writing for the electric field. You get this relation for transverse electric. And reflectance is just a absolute magnitude of this is squared. And when you plot reflectance for transverse magnetic, you get it vanishes at this angle. We call it Brewster's angle, and this is the angle that was where the dip was. But the transverse electric doesn't have any such thing. So for the external reflection, you get this. Now you do the same thing for the internal reflection. You would find you do transverse magnetic part still has a dip, but transverse electric part does not have the dip. And at the critical angle like this, you can see that if this is going to be less than 1 and this is less than 1, but at some point this will become imaginary, right? So whenever sine theta equals to n, beyond that it will become imaginary, and in that case what you have is this critical angle. At that point excuse me, everything gets completely reflected. So this is total internal reflection here. So if you have unpolarized, as I was saying, unpolarized will be kind of combination of these two, say half and half. Then you will get something like a dip, and it will be the full back there. And over here it's going to be dip at the, and over there it's going to be full beyond the critical point. So what to look at when this becomes tells you when that will this angle will be when numerator is 0, that's when this theta 1 or incidence angle for that incidence is what's the Brewster's angle, what we call Brewster's angle, and from there we can just read it off. Okay, so we say minus n square cosine theta Brewster square root of n square minus sine square theta Brewster equal to 0. And you can simplify it by putting this on the other side, and then you have an n to the power 4 cosine square theta Brewster equals to n square minus sine square theta Brewster okay, so I just went ahead and did the steps of calculation. So sine theta b is that, and you can think of this in a triangle like that, and from there you can clearly see that this side has to be 1, and so it's easy to write it like tangent of theta b equals to simply n over 1. So this is the formula for Brewster's angle. Now because n is a function of the wavelength of light, so this whole thing will depend on the wavelength of light. But when it comes to visible light, it's not very strong dependence normally, so we just ignore it. We just say, okay, I'm just going to use it for green light. Okay, so that's the Brewster's angle concept. I'm going to stop here. Now, hopefully, okay, so where we'll find Brewster's angle problems. So one of the problems is just they give n1 and n2 and find theta b. That basically is a really silly problem. Just theta b is arctangent n2 over n1. Okay, so that's not a very good problem. But other kind of problem is like they give you a scenario and they want to ask you what the polarization of the light will be. So suppose you have unpolarized light and it's shining on this. So there may be one ray like this, and there could be a ray like that, and there could be other rays like that. So let's look at these 3 rays, and here is a ray. This angle is Brewster's angle for this n1 and n2. So when this reflects at theta b, angle of incidence, angle of reflection, over here no transverse magnetic, right? Because if you remember from just earlier discussion, this will be just a transverse electric. What does transverse electric means? It means that if you have a, so this is the plane of incidence, reflected and transmitted. So transmitted electric field is pointed vertical to that. So that's the direction of electric field. So electric field is all going back and forth perpendicular to that. And magnetic field for this wave will be pointed this way. That will be the magnetic field. Of course, that's 90 degrees to the direction it is going. How about here? Here you'll have both transverse electric and transverse magnetic rays, because transmitted rays don't disappear. Okay. How about if this is another ray? So for this ray, you will have reflected like this. Now, you'll have both TE and TM in this, because TM didn't get disappeared over here. Similarly, over here, you'll have both TE and TM, because TM didn't disappear. So that's they might want to ask which way the electric field is pointed, what's the magnetic field pointed, when you have a reflected at Brewster's angle. So that's another interesting one to ask. Okay. Sometimes they say, okay, because this is, we know the polarized, I sent in unpolarized, but this is a polarized. So this is polarized as TE. That means we should be able to use this setup to produce a polarized light. Suppose I wanted to polarize light for some experiment, so this will be one way to do it. And that's why you want to know what's the polarization, how to tell the polarization here. Okay, is this the best way to produce polarized light? not actually. This is too inconvenient, and it's rarely used for that purpose. Okay, so this would be another way this is used as a setup is you may want to reflect off and send this to some other device here. So you're sending this in this device, and then if this is an experimental setup for using polarized light, and then we'll question about that device that's using the polarized light. So you know which kind of polarization you have actually sent in if you have set up like this. So that's another way Brewster's angle problem shows up. So I just thought of this after I recorded the main video, and maybe I'll try to insert it in my editing. Okay, I'm going to stop here. Have a good day.